Okay, so welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're very lucky to be joined by Matija Cuk, who's a new SETI PI. Matija got his Bachelor's of Science at the University of Belgrade in Serbia, and then did a Master's of Science and PhD at Cornell, where he studied the dynamics and origin of irregular satellites. Then he did postdocs at the University of British Columbia and at Harvard University. Much's research revolves around orbital evolution of small bodies, small binary asteroids is where he's published, and resonance capture of irregular satellites. And he's also interested in resonances in the Earth-Moon system, and that's what he's going to talk to us about today. So if you'll join me in welcoming Matija.
Thank you, again. So I'm relatively new at SETI, and this is the work I've done at Harvard, and I'm still there with one foot. And this is the work I'm doing with Sarah Stewart at Harvard. So first, I'll tell you a little bit about the giant impact hypothesis for the formation of the moon, which is the dominant theory right now. Then I'll discuss some problems with this theory that have some of which have been around for a long time, and some are recent, are having motivated by recent discoveries. Then I'll talk about how we can solve all these problems by having initially faster rotating Earth than in the standard model, and by following certain resonances. I'll explain what they are between Moon and the Sun. Then I'll talk a little bit about the second set of resonances involving Earth's core and the Moon, which is still a work in progress. And then I'll tell you what it means for our understanding of early Earth and the Moon. So, giant impact model of lunar formation is now the dominant way we think, the dominant idea about how the Moon formed. So, the idea is that the Earth, while it was being formed, suffered a late collision with a Mars-sized planet, or a protoplanet. And the collision between these two bodies, mantle material was launched into orbit around Earth, formed a ring, not unlike Saturn's ring in many ways, and which then coalesced into a single body, the Moon. And this model agrees with the amount of angular momentum in the Earth-Moon system, and explain how that works. And the important thing is that the Moon initially formed very close to Earth, according to this model, but we have other reasons to think so. And because of tides between Earth and the Moon has moved from being just a few radii away from Earth, being very close to Earth at formation, to 60 Earth radii, what it is now. Earth and the Moon are actually quite far apart for a planet-satellite system. Yes?
Is any, in this model of Mars, protoplanet, and the Earth, is there anything important about the approach direction of these two bodies? Were they kind of collinear and there was a soft collision, or were they like colliding opposite?
It's an off-axis collision. This is a simulation done by Robin Canup from Southwest Research Institute. So you can see the frames from the movie, that impactor hits Earth and the stuff flies around. For a while it forms a spiral arm and then forms into a disk. And this is the view from the side. So there are still some features in the disk, but basically it forms a ring. And from the side you can see that the ring is flat. So eventually things would form into a disk from which one body would accrete. So they did lots of these, and they came up with something that works, which is off-axis collision, and the body approaches relatively slowly. And sometimes people are suspicious that it's a bit too slowly, but I'll talk about that some more later. So how do the tides change the distance between Earth and the Moon? So this is an extremely simplistic view of how tides work. But the basic idea is that Earth is not perfectly round not only because of its rotation, but because of lunar gravity. So the moon the moon attracts all of Earth, but some parts are closer to the moon and some are further out. And since it follows an orbit around center of mass with the moon, all of Earth, the center of Earth, is in principle in free fall, in 0g, with regard to lunar gravity. But the part of the Earth that's closer to the moon is pulled stronger than average, while the part that's further out is pulled weaker than average. And since it's only the average attraction of the moon that's being matched by orbital motion of Earth, the close and far ends are being a little bit out of balance with the attraction of the moon, so the two bulges form, both in rock and the oceans. They're more dramatic in oceans, obviously. So if Earth did not rotate at all, these bulges would be aligned with the direction to the moon. However, since Earth is spinning, and both rock and oceans have a finite speed at which they can conform to gravity, these bulges are misaligned. And once you have misalignment of elongated body interacting with something else, you can get a torque between Earth and the moon. So what the moon does is torque the bulge on solid Earth and the oceans back to align with the moon, while the bulges torque the moon to move in the direction of Earth's rotation, which is also forward for lunar orbit. So Earth is being slowed down. The Earth is being pulled back, and the moon is being pulled forward, because Earth is spinning much faster than the moon goes around the Earth. So in the process, the momentum, the amount of spin, that is the angular momentum, is being transferred between Earth's rotation and lunar orbital motion. For the rotation, when you lose angular momentum, you just slow down. For the orbital motion, if you add angular momentum, according to Kepler's laws, you have to move to a higher orbit. So orbit of the moon grows while the spin of Earth is slowing down. And this is a reconstruction of what happened over the age of the system. Initially, Earth was spinning once in every 5 hours, and the moon was very close to Earth. And since then, the length of day has gotten much, much longer. A lunar orbital period, so this is lunar orbital period in days, and here is length of day in hours. Both of them have gotten much longer. And initially, Earth had most of the angular momentum, and very little of it was in the moon. Now, the angular momentum has moved from Earth to the moon, and now only 1/6 of the angular momentum is in Earth, and it keeps decreasing. Okay, so this is the dominant picture right now. So what are the current problems with the giant impact hypothesis? So most of the material that went into the disk around Earth that led to formation of the moon appears to come from the impactor, according to the simulations like the one I've showed you before. And that doesn't seem to square well with the composition of the moon as we know now. So the composition is one problem I'll talk about in some detail. The other problem is orbital inclination of the moon. Orbit of the moon is tilted right now and has always been tilted as far as we can tell. And if you form from a thin disk, like Saturn's rings, you end up with a body that's orbiting in the equatorial plane of the planet. So orbit of the moon should have been aligned with the equator when it formed, and it didn't seem to have been. Then also, the impact looks a bit fishy. The impactor seems to approach too slowly to Earth. This might or might not be a problem, but might be a clue that we are missing something in modeling this event. And also, to get where we are now, the impact has to be within 10 degrees of the plane of Earth's orbit. So the impactor has to really come in along the orbit of the Earth, not out of plane. And given how orbits of the planets are, how much they are inclined, it's more likely that impactor would come out of plane than in the plane. So that's another clue that maybe there are some other processes acting here that we are not really seeing right now. So biggest problem with giant impact hypothesis are the oxygen isotopes of Earth and the moon. So here you have this fractionation line. So, I do orbits. So I believe what geochemics people tell me. And if you have the material from the same body, it should all cluster along one of these lines. So the red points are for Mars, the blue ones are for Earth and the Moon. So you can see that Earth and the Moon cluster on one line just like if they were one body, while Mars is significantly different. Yes? I don't know here. This is, but quite a few. And the error bars on this have been shrinking over the time as better techniques are used on moon rocks. So when the giant impact was first proposed, the error bars were huge, and it wasn't clear that the Moon is much closer to Earth than Mars. But now the error bars have shrunk enough that basically they're the size of symbols on this plot. And so the idea is that if different planets in the inner solar system had different isotopic composition, just from a random mix of materials they form from, the impactor should have been about, on average, about as different from Earth as actual Mars is. And we should see some of that difference in the composition of the Moon if the impactor was the main source of lunar material. But we don't see that. It looks like lunar material was derived from Earth. And that is that is a conundrum. And then the other problem, well, the rest of the problem is that it's not just oxygen. People have come up with theories that maybe you can evaporate some of the oxygen and have a longer-lived disk that would lose some of the volatiles. Because oxygen is often gas. You can easily lose it. However, there are lots of other isotopes that behave the same way. And the real smoking gun is tungsten, which some of the isotopes of which are radiogenic. So not only do they not only are they the same between Earth and the Moon, but it means that if you want to make them the same without Moon being really derived from Earth, this other body not only was made of the same stuff as Earth, but it had the same amount of mixing between the core and the mantle as Earth, which is impossible for a body of different sizes. Geophysics and geochemistry people tell me, because rubidium and tungsten, which are connected through the decay, have different places they want to go. One wants to go into the core, and the other one into the mantle. So as the rubidium decays, and you have this separation into core and the mantle, the amount of tungsten that stays in Earth materials or materials of any planet doesn't just tell you how much rubidium there was in the beginning, but how did the planet evolve during the early evolution. And it seems that Earth and the Moon evolved the same. And the only conclusion is that the Moon was just formed from Earth material and did not come from and the material did not come from a different body. So this is a rather complex argument, but it seems to be rather solid argument for Moon being originally part of Earth. And this is from one of the previous, from one of the simulations I've showed you before. The final location of the material is plotted on the original location of the material. So the stuff that goes into disk and eventually forms the Moon is here colored yellow. So you can see most of it comes from the impactor. This is just before the impact in this simulation. And this simulation is somewhat typical of all the ones that Robin Cranab did. She did some of the best and most influential simulations of giant impact so far. So to talk about lunar inclination, which is a completely separate problem, I have to remind you what inclination is. So you have an orbit and a reference plane. So this horizontal plane is some reference plane. For us, it's going to be orbit around the Sun, Earth's orbit around the Sun. And you have an orbit, say lunar orbit around Earth. The inclination is the angle between the plane of the orbit and reference plane. And I would use this opportunity to also show you what the longitude of pericenter is. So pericenter, or in the case of lunar orbit, we call it perigee, is the point of closest approach to Earth. And the angle between some reference direction and the pericenter is so-called longitude of pericenter, or longitude of perigee. And we'll talk about it some more. Basically, that's the angle between reference direction and the long axis of the orbit. Will become relevant later. But so first, inclination. So this is a different simulation by Ichiro Kokubo. This is not a hydrocode. This is simulation with lots of small bodies, so you can run it for longer. And they basically divided up the cloud that's left after one of those impact simulations and just made it to lots of small particles and let them settle in orbit around Earth and collide with each other. So after a while, they settle. By the way, this is not exactly to, it is to scale, okay. And they settle down and keep forming large bodies, but all of these large bodies are in the plane because that's what the disk particles want to do when colliding with each other. And in the end, when they form a moon, eventually there will be only one moon left. What you have is the body that's orbiting in the plane of the equator. And this happens everywhere where you have a disk around the spinning planet, because planet is slightly flattened and the gravity field is not uniform. And the disk material always wants to settle eventually around the equator, which is the kind of plane of symmetry for the gravity field. Then this is rather arcane, but there is something called Laplace plane. As I said, the reference plane from which you measure inclination will be in this talk, the orbit of Earth around the Sun. But originally, the disk material settles around the equatorial plane. And as the tides move moon out, what is preserved is not its inclination to equator or the ecliptic, the orbit around the Sun, but what is preserved is its inclination to so-called Laplace plane, which is a plane that starts out as the equator of Earth and kind of gradually moves over to the plane of orbit around the Sun. And if you do this migration slowly, as tides are slow, you preserve inclination to whatever the reference plane is, well, to whatever local Laplace plane is. So if you start with inclined orbit to equator, you're going to end up, after tidal evolution, with the orbit that's inclined to the ecliptic, the orbit around the Sun. If you start with the orbit that's in the plane of the equator, you end up with the orbit that presently should have no inclination. Okay, so this is one reconstruction of the inclination evolution of the moon by computer simulation. So right now we are here, and this is inclination of the moon relative to the ecliptic. So right now it's constant. As you move closer to the Earth, the behavior becomes more complicated because you have three planes here: the orbit itself, orbit of the moon, then orbit of the Earth, and the equator. And they all precess in complicated ways around each other. But when you're close to Earth, it's the thickness of this line. So they didn't shade all of this region, but this is basically where the moon is at different times of its cycle. The thickness of this thick line in the beginning is the inclination. And when you get further out, it is just what is plotted this inclination is the inclination to ecliptic. But early on, if you have a plot like this, the real inclination is the semi-thickness of the line. And you can see from this that since this is from 0 to 20 degrees, the semi-thickness of the line early on is approaching 10 degrees at the formation of the moon. So moon formed with an inclination of about 10 degrees to the equator. So how do we solve this problem with both composition and inclination of the moon? So one way to form moon from Earth material is have a faster spinning Earth. And if you either deliver lots of spin in a collision or hit faster spinning Earth, either way, fast spinning Earth material will have easier time going into orbit and contribute more to the moon. So this is similar to fission, only that there still is an impact, because we know impacts are frequent and convenient for this purpose. So if you have faster spinning Earth, with a spin closer to 2.5 hours, the stuff on the equator is spinning so fast that it's not really far from going into orbit. So you just needed to give it a little bit more kick, and much more stuff would end up in orbit than in the conventional reconstruction that Earth was spinning every 5 hours. But of course, there is a problem. If all the reconstructions tell us that Earth was spinning once in 5 hours, how do we end up, if we start with a fast spinning Earth, how do we end up where we are now? Or more technically, how do we lose angular momentum? So one way to do it are resonances with the sun. So orbital resonance is a phenomenon in which two periods in the system are the same. Two periods of two different things, two different kinds of motion. And when the periods are the same, they can communicate with each other very strongly. Although otherwise they might be rather isolated from each other. So one resonance that was found was so-called advection resonance, that early on the moon's orbit could get into resonance with the sun. And I'll show how it works. And since then you communicate between the sun and the moon, the orbit of Earth around the sun and the orbit of the moon, you can extract angular momentum from moon's orbit into the orbit around the sun. And the other thing that can happen is that if you have a friction, if you have a notable friction between Earth's core and the mantle, in some cases you can lose some amount of angular momentum also. And although in classical reconstruction, you never get significant events of misalignment between core and the mantle. But you can also get resonances between the nutation of the core, I'll explain what it is, and the moon, if you have a faster rotation. So both kinds of resonances I have here, resonances between moon and the sun, and the core and the moon, could be much more significant if you start with the faster spinning Earth. So we wrote a symbolic integrator. So this is for the people who do exactly the same thing I do. If you don't know what this is fine. But we try to put everything anybody else put in so far. And it seems to work. OK, so this is our simulation with the Earth spinning every 2.5 hours. And this is distance of the Earth to the moon, or technically same major axis. So we start at 3 Earth radii, which is really close, about as close as moon could have been originally. And it shoots out really fast. This is in kilo years, thousands of years. So since the system is billions of years old, this is really, really quick. Because tides are always very strong when two bodies are really close. Now tidal evolution is slow, but back then it was really, really fast. So moon shoots out, but then gets stuck, doesn't do anything for a while between these 2 points, E1 and E2. For a long time, and then continues. And if you actually cut these two parts of a curve, they match more or less. There's this shift in the middle where something else is happening. So this is this so-called advection resonance. And this is what eccentricity of lunar orbit means. So eccentricity is measure of elongation of the orbit. If you have circular orbit, it's 0 right here. Orbit with eccentricity of 0.5 is rather egg-shaped and off-center. So at the moment E1, eccentricity shoots up really fast, really high. Then it's stuck at a more or less constant value for a while, and then damps down. So this damping behavior, like the basically declining curve like this, is typical of what happens if you let the tides do their job. So, but in between, something else is happening: the shooting up and then slow decay. So this is the resonance between Earth and the moon. Sorry, between the moon and the sun. And this is how it works. Sun goes around Earth. Well, this is Ptolemaic view, OK? I'm not claiming that Earth is actually the center of the universe. But it's a really convenient way of looking at these things. So let's pretend that sun goes around Earth once every year. In this case, counterclockwise, viewed from the north. And lunar orbit. So we don't care where the moon is instantaneously, because it goes around really fast. But the lunar orbit is also shifting around at a certain rate. So when you are at that point, E1, that was in our simulation at, was it 7 Earth radii? The rate of rotation of the whole orbit, what we call precession, is 1 year. That means that if the long axis gets aligned with the sun, they'll stay stuck in the same configuration. And so these two motions are independent of each other in principle. The solar relative motion around Earth and precession of lunar orbit. But if they end up having the same period at some point. And the period of precession of lunar orbit keeps changing because the size of the orbit keeps changing. And then the other parameters keep changing over time of evolution. So just at one point, it's 1 year, and it can get stuck in this resonance with the sun. And then sun and lunar orbit can communicate and can trade angular momentum. So this is another view of looking at it. So this is distance versus eccentricity. So the track goes like this. You're at low eccentricity for a while, you hit this resonance, then you shoot up on this track. This is the line along which you precess once per year. And then you have this more complicated branch here. Has to do with lunar and Earth tides being in balance. And eventually you get out of the resonance and float out. Continue normal evolution. And this is what happens to Earth's spin period. We start with 2.5 hours. It slows down a little bit up to point E1, then slows down quite a bit to 4 hours, and then continues slow evolution. And this is angular momentum. So this is the most important measure of what's going on. So this is orbital angular momentum of Earth, and this is orbital angular momentum, spin angular momentum of Earth. Units are how much, the unit is the maximum angular momentum Earth could have ever had. Basically, if it's spinning every hour and a half. At angular momentum of 1 means that Earth is just flying apart. So Earth starts at 55% of that. So a large chunk of what it needs to fly apart. And you can see in the beginning, these two are mirror images of each other, the Earth curve and the Moon curve. And that's because any angular momentum that goes away from Earth by tides has to go into the Moon. So the Moon gains angular momentum while Earth is losing it. Then there is this resonance phase when Earth is slowing down, but Moon does nothing. So what's happening is that tides are giving spin from Earth to the Moon. Lunar orbit wants to become bigger, but it's stuck in this relationship with the sun. So then Earth-Sun orbit has enormous amount of angular momentum compared to Earth-Moon orbit. So if these two are communicating, it's a little bit like having a little stream flowing to the ocean or something. Any angular momentum excess angular momentum that Moon is getting from Earth is going to flow into orbit around the sun, so that the two could maintain this resonance relationship for a while. So this angular momentum is basically gone from the system. It's now gone into orbit around the sun, and don't worry, it hasn't changed the distance from the sun. It's really, really minute compared to size of lunar orbit, so size of Earth's orbit around the sun. But so when we end the resonance, then the two curves become mirror images of each other again. And whatever Earth loses, the Moon has to gain. Yes?
Is it your feeling that all that angular momentum originated with the initial formation of the Earth, or was it imparted to it by the colliding body? Repeat the question.
Yes, this is an excellent question. So all this angular momentum, was it originally on Earth before the impact, or was it mostly imparted by the impact itself? And we don't know that. We haven't modeled it yet. My guess it is a mix. Definitely Earth was spinning before the impact, and impact itself contributed a large chunk. So probably both. Okay, so this is view of lunar inclination. So I like to plot it against the relative to the orbit around the sun. So we start at 40 degrees. So what does it mean? That means that in this simulation, the impact happened 40 degrees relative to orbit around the sun, and both Earth's equator and lunar orbit originally are under this angle. So we relax this requirement that they have to start close to the plane of the ecliptic, because we want to see what happens. If we start them different, would they evolve to where they are now? And initially there is no inclination. You can see that in this kind of plot, the inclination of orbit to the equator is just the semi-thickness of the line here. So originally there is no inclination because the line is just very thin. Then very early on you get this kick to about 2 degrees. This is the point where there is a different resonance, but you don't get stuck in it. You just cross it quickly, and it gives a kick to inclination of the Moon. And then there is a second resonance here. So this one I like to take to call tip-over resonance, and this is a mixed resonance that depends both on inclination and eccentricity. But basically, in the end, you can see that you end up with something that's on the order of 3 degrees inclination at the end of the simulation. What we get in the end often varies between, depending on how fast the Earth is spinning, how strong are Earth tides relative to moon tides, what the original tilt of the system is. But we typically get, for most parameters, we get a few degrees inclination. And we have to get to something like 10. So we get some inclination, but not enough. But this might be the part of the story. And this is the picture in distance versus inclination. It's really complicated, and unless you're into orbital dynamics, this is not a better way of looking at it. OK, so let's summarize this first part. So this resonance has been known before. But the difference now is that when Earth is spinning faster, this resonance is encountered further out, a bit later, which makes it much stronger because tides slow down by that point. So whenever you go through a resonance more slowly, its effect on the orbit is stronger. So this resonance happens when the perigee precession period of the lunar orbit is 1 year. Angular momentum goes from lunar orbit to the sun. But this angular momentum originally is coming from Earth. So Earth spins down, the moon is standing in place, and the sun gains the angular momentum. And the moon becomes very eccentric at a point, but then it damps down. And we typically acquire a small inclination, up to 3 degrees, more typically 2. OK, so we end up with Earth that's much more tilted than it should be. There's still a little bit too much angular momentum. We could take care of that, actually. We can match the angular momentum at this point. But the tilt of the Earth and the inclination of the moon are not right yet, because the tilt is too large for Earth, and the inclination of the moon is too small. But if you still had too much angular momentum, you might run into a different kind of resonance between the wobble of Earth's core and lunar orbit. So Earth, to the first degree, is made of solid mantle and liquid core. There is a solid inner core, but we'll ignore that. Both of them are elliptical. In a sense, both of them are a bit squished at the poles and fat at the equator, because both our core and the mantle are spinning at about the same rate. But what happens that if you tip a core out of alignment with the mantle for some reason, whatever the reason might be, if they're a little bit tilted out of alignment, the core will always try to have a shape that matches its instantaneous spin axis. Because if you shift the north pole of the core a little bit from north pole of the mantle, then the equatorial bulge is also going to be shifted a little bit. And core, being liquid, responds to this shift in the spin axis position instantaneously. The mantle is more solid. It's pretty solid in a short time scale. So mantle doesn't care. The hole that is there to accommodate the core stays the same. And it's aligned with the pole of the mantle, pole in the equator of the mantle, not that of the core. So you have some pushing around. The core wants to make space for itself with its slightly different shape, and the mantle doesn't let it. So the two are basically pushing against each other, which results in a torque on the core. And the end result is the core and the mantle wobble around each other with certain period that depends on the spin rate and aspirant cubed, basically. And so right now, the period of this wobble of core around the mantle is about 430 days. And this is the way the core and mantle are stuck to each other. So if you tilt the core a little bit out of the alignment with the mantle, instead of staying misaligned, it wobbles around the mantle and follows what mantle does, and eventually friction slows down this wobble and damps it down. So the main cause of misalignment right now is the precession of Earth, because really the mantle is much more squished than the core. And the sun and the moon, when they tug on the equatorial bulge of Earth, they tug on the mantle, and not really the core. So during all this long-term wobble of Earth, which we call precession of the equinoxes, it's the mantle that's moving and it's pulling the core along. But core doesn't respond right away to it, so it always leads to a certain amount of misalignment and wobble around each other. And in the course of this process, wobble is being damped by the friction between the two components. And it's a rather complex argument, but it's the spin that's out of the plane of the orbit around the sun that's being damped. So the bottom line is this process should damp tilt of Earth, the obliquity of Earth. And it cannot really change the spin that's in the plane of the orbit, but you can only change the spin that's out of the plane, which translates to the fact that it can damp the tilt. But if Earth was not tilted, this couldn't do anything to our core in the mantle. And since the rate of this wobble is proportional to the cube of the spin rate, you can see that if Earth was spinning faster at some point than we think, then all these resonances are shifted, and you can get into certain kinds of resonant arrangements with the moon. So if you just do it with the present angular momentum and extrapolate back to the formation, the moon and the core missed each other in terms of resonances. This period here of the wobble of core around the mantle was never equal to 1 or half or some fraction of the month. It was always longer than the month, significantly longer than the month. But if you spin Earth faster early on, you can get into one-to-one relationship between the month and the wobble of the core around the mantle. So the resonance I'm going to show here is basically the wobble of the core measured from lunar orbit, and that's a complicated issue. How you define long-term lunar orbit? But the wobble relative to the lunar orbit is the period is equal to the orbital period of the moon. So every time the orbit of the moon and the core are aligned the same way, moon is at its closest approach to Earth. And this leads to periodic kicks of lunar gravity on the core and leads to large-scale misalignment between Earth's core and the mantle. Okay, so since this resonance, the wobble period of the core, which is technically called free core nutation, depends on spin, and if you want to get it in resonance with lunar orbital period, you can make this plot. On one side is how fast Earth is spinning. On the other axis you have how far is moon out there, how far out is the moon. So you can plot the lines of constant angular momentum. So on all these solid lines, angular momentum is the same. And if you start on any one of these solid lines, you're going to move down and to the right. And now we are here. So the standard reconstruction was that the system moved along this line. So early on, Earth was spinning faster. So on top is the fast spin, here it's slow spin, and moon was much closer in. And this blue line, the blue dotted line, is where the resonance is. So if the system crosses the dotted line, it hits the resonance. So if the moon was moving, if there was more angular momentum in the system, it could have grazed the resonance, that's the blue line. However, the relationship between spin rate and the wobble might have been different early on when Earth's mantle was not completely solid. So you can have a whole family of these curved dotted lines in the past. And whatever the original track of the moon was, it could have met one of those lines. And then you have the complicated shift. So tides want to move you this way, and all of these dotted lines would want to move to the bottom left and converge on the blue one. So you get a very complicated motion. And I'll show you what the moon does on this plot, so it will make more sense. So what we did was put the moon just before one of these resonances and let the tides evolve it. And if it hits this resonance with the core, would anything happen to core or the moon? Well, it does. This is offset in degrees from of core from the mantle. So first they're aligned, and then when you get to this point A, which is the resonance, when the 1 month is equal to the wobble period of the core gets 2 degrees misaligned with the mantle and stays there. So this is 1 million years, the first million years of the resonance. What happens with the lunar distance? So this is very zoomed in. This is about 20 Earth radii. So this all happens about 10 million years in the age of the system. Moon moves out, and then when it hits the resonance, starts moving in. So the resonance with the core stops the growth of the orbit, but makes even the moon move slightly inwards. And the same resonance makes the moon very eccentric. So the electricity shoots up very fast after the point of the resonance. If you're into orbital dynamics, I can explain why eccentricity has to grow. But the theory here matches well what computer puts out. So we are happy with that. And this is the spin period of Earth. At this point, it's 5 hours. So it's still faster than it should have been in the normal reconstruction. We move up slow. Well, the period gets longer and longer slowly due to tides. But then once we enter the resonance, there's a knee, and the dissipation becomes much faster. So it slows down much faster, because here it's not just the tides, it's also the core-mantle interaction that slows down the spin. And this is the obliquity of Earth. As you can see, it goes down at first. So the core-mantle interaction is capable of dropping the obliquity. So at this point, it's like really high. We have it at 46 degrees. But if this resonance lasts for tens of millions of years, we can bring it down, possibly. So this was the track on this plot that I envisioned for the moon. So you move by tides along a solid line, and when you hit the resonance can scoot you down, because the whole resonance, the whole dotted line is moving down to converge on the blue dotted line. And then after that, you cannot, while in resonance, you cannot cross the dotted line. So you have to move along it until you get to the point where they touch, and you can get free and continue evolving. Now, this little branch here is that when you end the evolution through the resonance, the moon is going to be very, very eccentric. So the only way, the moon is going to be very eccentric. And once the resonance is gone, the tides are going to decrease the eccentricity. And so I'm calling these lines the lines of constant angular momentum, but they're really not, because angular momentum depends not only on the spin of Earth and the distance of the moon, but also eccentricity. So if you damp eccentricity, you shift slightly to a different line, and we just matched all this to the present system, so that when you're done with all this, you end up on the curve that leads to the present. So that's the idea. And we're not quite there yet with the numerical results, mostly because our integrator, the computer, needs to run this slow enough that it can resolve the rotation of the Earth, that is hours. And this whole process takes tens of millions of years, so it's really slow. And so we try different tilts of Earth early on. We are trying different strength of core-mantle friction, a different strength of tides, different rate of mantle solidification. So they're somewhere halfway through the exploration. So what we can do is a long-term capture. So we can have this resonance be stable for a long time. But so far, we haven't been able to produce enough inclination, and we are looking at other ways of doing it. Probably, we are converging to the opinion that at the point when this resonance happened, Earth solidified relatively fast compared to lunar tidal evolution, and that might work. But here is one that I just printed out yesterday. So this is in years, you can't see very well. So it's 1.2 times 10 to the 7. So basically this is 12 million years here. This is how far we got with one of these. And you can see that this is a tilt of the core, and the wobble, well, the jitter on top of the wobble is small at first but gets bigger and then goes down again. And We still have to figure out why it does all these things. But also this, the inward motion of the moon stops at some point and the moon keeps going back out. And eccentricity kind of stabilizes. We understand this part quite well. It follows the predictable curve. So I was hoping a couple of months back that I'll have more done for the second part than I have, but we can still say a few things about what all these resonances mean for the Earth-Moon system evolution. So if you consider an initially fast-spinning Earth, early resonances with the Sun definitely can alter angular momentum. And so in a way we can solve the composition problem. We do not solve the inclination problem yet. We haven't solved it yet. The second resonance between Earth's core and the moon could do it. But it's interesting, it's important to point out that giant impact hasn't solved the inclination problem either. Has been around for a long time, and maybe there's something else that might resolve it. But just in the terms of, can you take angular momentum away from Earth after formation and use that to explain why a moon looks like Earth? Well, that Earth was spinning really fast during the impact and later lost that spin. We can do that. And right now we are just keep running more simulations, and I think that given that it works so far, that the answer to the inclination problem is also in the same set of resonances, and that's something that I'll more about next year. Thank you.
Matija, can I start with a question? So the composition problem, the faster spinning Earth is helping that because more material is coming off the Earth when the impactor comes in?
That's the idea, that it's always easier to launch stuff into orbit from a faster spinning. Like whenever I have collisions, the body that's faster spinning is easier to disrupt. That has been done on smaller scales for asteroids. So we haven't really done that part, but it kind of, the physics scale is pretty well, so that's well expected.
You still have to hide away the initial impactor if it's not from the Earth, right?
Well, it's interesting.
Could that be in
if you
the core
right now, formally, it could be less than 10. If less than 10%, it matches the constraints. I don't know how it's going to change once we get even better error bars, but so far it doesn't seem to be the problem to have a little bit of it. And also, previous models had much of the impactor going into orbit because they needed stuff going into orbit. Now, if the collision was more central, maybe the impactor would just get absorbed instead of basically being captured by collision. Material, an impactor after it hits Earth just goes into orbit, like misses Earth, really. It's a lot, well, some of you might have been in Eric Asfog's talks. So he showed lots of those simulations that it's basically a capture by collision. These will be different. The impactor will be completely absorbed, but it would give a kick to Earth material in front of it that could go into orbit. So that's the idea, but we haven't done it yet.
Okay. And they'd be homogenized more than in that process?
Yeah, well, we don't know how big the impactor was because the Mars-sized impactor worked well for the kind of giant impact that gives you the present angular momentum. So we really don't know how big it was, or how fast it was moving, or how fast the Earth was spinning before that.
Quick question, then a little longer one. In these calculations, do you have to do several with nearby initial conditions because of chaos, or is it pretty well defined?
There's nothing really chaotic here in the sense that
passage through resonance is deterministic.
Oh,
process.
yes. Well, okay. So compared to what two-man wisdom did before, since we have a Q of Earth about 100. So when we get to the resonance, it's moving really slowly because this is at 7 Earth radii, not 4. So we don't have the problem that capturing the resonance probabilistic. It's so probable that we don't have to worry about that.
And the second one is the solid mantle.
Yeah.
I would think that it's going to take hundreds of millions of years, if not longer. So way longer than what you're talking about for the mantle to be solid. In fact, it's only solid in the sense of short time scales now. But I'm wondering what the viscosity is that makes it solid on the relevant time scale, and whether anyone, you or anyone else here, knows how long it would take to cool from a very hot state to get that lower mantle viscosity.
Well, we had actually a seminar about that at Harvard last semester. So I know more about it than I did before. So one number people are throwing around for the overall mantle solidification is 5 million years. So it's not that off. Now, the lowermost mantle was always solid, just because the way the silicates behave under those pressures and temperatures. So even at its hottest, there should have been a solid material down there. And one point where it might enter into like the whole picture of Earth evolution is that lower mantle seems to have a different composition of upper mantle. And if Earth was completely liquid early on, it wouldn't have happened. So, and we want to have lower mantle be solid from the very beginning, because there's no core mantle boundary unless you have some solid mantle. So 10 million years seems like a reasonable thing. And of course, the way we're going to do it is we're going to run it with different things, see what works, and then reverse engineer the geophysics we need. But 10 million years sounds reasonable. I've heard 5 being thrown around. Yes.
It's 1 or 2 million years is probably the best.
Okay.
It's determined by the rate at which you can cool the system.
Okay.
A point of clarification and then a question. When you say the moon at 3 Earth radii, is that from the center or from the surface of the Earth?
From the center.
From the center. So it was very close to the Roche limit.
Yes.
Particularly considering the moon's a lower density than
Yes.
the Earth. Yeah. Okay. And then the other question was, since the impactor, because it impacted the Earth, it is about the same distance from the sun as the Earth. And could that have been the thing that determined the oxygen ratios and tungsten isotope ratios, rather than, so that from the beginning, the impactor had about the same oxygen ratios as the Earth, not as Mars?
Well, there are two answers to this. One is that it doesn't seem to be a smooth correlation between oxygen isotope and distance from the sun, in the sense that when we look at different sources of meteorites we have, so we don't know what Venus is made of, but we have meteorites from Mars and Vesta and other asteroids. It doesn't seem to be a clear correlation, as far as you can tell, of how far out you are and what the oxygen isotope ratio is. And the big picture is that when you form inner planets, big chunks fly around. So some of the material that Earth is made of started out closer to Mercury, some started out maybe even beyond Mars. So when you make a mix in few large last impacts, you get more of a random jigsaw puzzle of compositions from the inner solar system. So you wouldn't expect the impactor to be the same way. So that's the theory. The more direct constraint is the tungsten, is that tungsten ratios depend not only on the initial composition, but also on the evolution of the planet, like when the core was formed and when you separated the core and the mantle. And if that's the same, then it looks like it's Earth material rather than just, you have to be a planet that's the same initial composition and the same size, and that's really hard. Yes.
Your premise that you're working on here, as I get it, is primarily mechanical things like that. Do you incorporate in any way magnetism and electricity and the other planets and how they impact? You've only talked about the sun and the moon and the Earth, and occasionally thrown in Mars.
Yeah, well, the forces, so magnetic fields tend to affect smaller bodies more. It's just they have, more charge or more magnetic moment per mass. When it comes to things that are the size of Earth, just gravity is so much stronger than magnetic forces, so they don't really affect overall motion of Earth and the moon. Now, I was talking about core-mantle friction. Some of it is magnetic. It's hidden in the model, and it probably was very different early on. So we feel kind of free to vary it and see what comes out. Yeah, but so in the interior of Earth, yes, magnetic fields are very important. But when it comes to overall motion of large planets, they don't affect much. Yeah.
If we assume a fast spinning Earth following a giant impact, which would create enough debris to cause a moon to form, I understand that we need to remove a significant amount of the angular energy from the Earth, and that you're proposing that that occurs via resonance with the sun. Is it also possible that a different force could enter the system via maybe a smaller impactor, which would have the principal effect not of creating more debris, but of striking the Earth in a way which reduced its angular momentum? Have you considered that, or is that an option?
Well, people have tried doing that for the inclination. And so there were large impacts on Earth following formation of the moon, probably. Like one reason why you need that is the delivery of highly siderophile elements. So to the first degree, Earth is differentiated in the core and the mantle, and certain elements like being together with iron and assigned to the core. But when you look at Earth's mantle, there is still some amount of iron-loving minerals, iron-loving elements in the mantle. And the simplest explanation is that after the Earth divided into core and the mantle, you added some more small bodies in bulk, and added these hydroxylophile elements to Earth. And I think that the impactor wasn't bigger than about the size of the moon. So that if you put everything in one body, it's about the size of the moon. And if you hit at reasonable speeds, you don't get just enough angular momentum. There was an idea that you can change the tilt of Earth enough to form inclination on the moon. But that has time constraints, because then you have to time it right after the first impact when it's sensitive. But an overall change in the spin, so yeah, you would need it to be Mars size or larger for that. And that thing hasn't happened, as far as we can tell. Yep.
Sorry, we got a question back here.
Hi. How would you like to make a comment on how the orange material that was finally analyzed seems to indicate 100 times the moisture inside the moon than previously thought? I guess this is Apollo 17 stuff, some nicknamed Tang.
Yeah, so one thing about the volatile content. So I don't know much about this, I just do orbit. But I can tell you what Sarah Stewart says, who does impacts, is that often lack of volatiles has been assigned to impacts. For example, composition of Mercury, or the fact that moon is we thought moon was dry. But she says that that's kind of hand waving. It hasn't been done, actually. In some simulations, if things happen fast enough, you don't have time to vaporize stuff and have it escape if it reaccretes really fast. So now we are surprised that Mercury might have more volatiles from Messenger. And she goes around telling people, nobody really did it. People have been saying that there shouldn't be volatiles because of impacts, but it was kind of just, they used the word impact to cover what they thought was there. So how that affects Apollo 17 glasses, I have no idea.
When you write down your Hamiltonian in a symplectic integrator, I didn't really get how many degrees of freedom you have in there.
Oh, a lot.
Right.
Well, strictly speaking, we have only 3 bodies, really. So, and Earth's orbit around the sun is given. So it has no degrees of, we can choose where it started at, but that's about it.
Right, because what follows from this question is the following: is somehow there is coupling between angular momentums of the different bodies, and I'm not sure if you include the detail or not. And this is important because we invoke some kind of resonance, but the width of resonance has to do with the friction, but also the coupling between the different degrees of freedom. So to just say that the resonance is efficient is not enough. You need to know how wide the resonance is in some way, right?
I'm not sure I follow, but this is a direct, so we do not...
You can just say, resonance takes place, because
resonance take place. It's true, but the resonance can be smoothed over if it is very wide.
Well,
And that is written in Hamiltonian somehow, right?
well, we don't actually start from Hamiltonian. We start from the from direct forces on the system. So
the forces are modeled.
So symplectic means, okay, so the symplectic means something in analytical mechanics, but in this case, it just means that perturbations are treated differently from the Keplerian orbit, which makes for the more stable system. But really, this is direct numerical simulation, so which means that everything is done in kicks to the actual bodies. There is no...
But symplectic means you conserve energy.
Yes.
Right.
Yes. Yeah, but like it's as model free as we can get in orbital mechanics at this point, in terms of that we. Okay. Yeah.
One more question.
Uh-huh.
One possible way the whole system could lose momentum is a wandering planet scenario. If the solar system as a whole lost one or more bodies, and then the coupling would affect your resonances, and you'd only need a small amount.
Yes, but there is really no good way of coupling Earth-Moon system to planetary orbits. So, like for example, interaction in the orbits of the planets, which shouldn't have happened for Earth but happens for Mars, can change the tilt of the spin, of spin axis, but doesn't actually change the rate of spin. Also, in the flybys between, even if you have some really dramatic flyby between Earth and something else, which would really mess up things, you don't change the spin that much. People have tried to do that for something like Nice model, where really interesting things happen, and they found no, as the planets fly by each other, since they're symmetric, that is flattened rather than triaxial, you don't get much spin up. So we don't think first that inner solar system had encounters with anything huge, and even if it did, and it didn't get disrupted, it's really hard to spin up something that's almost liquid and flattened rather than elongated.
System as a whole losing one. The whole solar system.
Yeah, so but orbits would exchanging momentum, but it's very hard to couple orbits and spins. Spins precess, but you cannot really change the spin rate as opposed to spin direction or tilt.
Okay, well, I hope you've all enjoyed your orbital masterclass today. Please join me in thanking Matija. Here's a special note.